Okay, so today is all about what questions you have. Do you have any questions from previous tests? Previous chapters, the last few chapters. What do you got? What do you got? Prepare for the final. Anybody scheduled a final exam yet?
A question 3 on
Exam 6 through 10,
exam 6 through 10.
question 3. Yes. So they're pushing with a horizontal force of 180, so that's this force right here, right? It moves forward at a 23 meters at a constant velocity at points. So right away, there are some things we can know. If it's going at a constant velocity, what is the total sum of the forces? Remember, if you have an overall force, what happens to the car according to Newton? Force equals mass times, it accelerates, right? If it's at a constant velocity, is it accelerating? No. So what do we know? If we add all the forces together, are we going to have any left over? No. So if this force pushing this way is 180 newtons, what does this frictional force have to equal? If those two have to add to zero. Negative 180, right? So you're going to have a negative 180 frictional force. Now that's not one of the answers, but it's related to one of the answers, right? So we now know what the frictional force is negative 180 newtons. And it wants to know what is the work done by each of the forces. The work done by the pushing force, the work is equal to the force times the distance that moves in that direction of the force, right? And since it's moving in the direction of the push, then you take 180 newtons, multiply it by the distance, which is 23 meters, and you're done. For the gravitational force, does it move up and down? Does the car move up and down? No. Force equal or work equals force times distance, and if it doesn't move in that direction, then what is the work done by the gravitational force? Zero. And what's the work done by the normal force, which is in the opposite direction? Zero, right? And then the frictional force, it does do some work because it's moving in the opposite direction of the friction, but that one's going to end up being negative work done. So the frictional force does negative work on the car, takes energy away from the car, and that happens to be the same as the force done as the pushing force, just negative, right? Same work done as the pushing force. Yeah, you're probably getting pretty used to the volume of shoes. I bought these shoes for like cheap, and they're like supposedly expensive shoes, like choppers. And man, they have thick soles, they're like wearing boots. But I guess they'll last forever. Who else has a question?
I have a question on chapter 17.
Chapter 17, okay. What do we got?
Question 17?
Question 17 on 17. All right. You hear a sound at 69 decibels. What is the sound intensity level if the intensity of the sound is doubled? So this one is a little bit tricky because there is a way to do the math, but it's easier to just look at the book. So sound intensity level, which is under 17.3. We go down here and we learn about intensity of wave, and then we learn about the decibel system. So here you could actually just double the intensity, put 2 times I over I naught and figure it out that way. But it's much easier to go down here to this little table and say, if the intensity level is doubled, in other words, it's 2 times what it was, then it increases by 3 decibels. And so if you started off with 69 decibels, then you add 3 decibels to that for double, and it will give you 72 decibels. That make sense? So because it's a decibel scale, decibel means that it's using this logarithm thing. Because it uses this funky logarithm function to calculate it, it's not going to, if you want to double your intensity, that's not going to double your decibels. It's just going to increase the decibels a little bit. Okay? So you could do the math here if you wanted to, but it's just easier to look it up. And so you look it up here and you say intensity 2 over intensity 1. In other words, your new intensity, which is intensity 2, divided by intensity 1, you get 2, which means your new intensity is double what it used to be, right? And then that is equivalent to an increase in 3 decibels on the decibel scale. So if you go back to the homework, it says we started at 69 decibels. If you want to increase the intensity by double, then you have to add 3 decibels to this. So your new decibel level would be 72. So 72 decibels is twice as intense as 69 decibels. Now, if you want to go 10 times the 10 times the intensity level, then that increases it by 10 decibels. So if you go from 69 to 79 decibels, that's 10 times bigger. And it's not linear, obviously. So you can use this chart. If it was going to be 5 times as intense, then you would add 7 decibels. If it was 5 times less intense, 5 times quieter, then it would subtract 7 decibels from your decibel scale.
And then I had the 16 on that one as well, but not
16. So what is the sound intensity level of sound with an intensity of 2.5 times 10 to the negative 7 watts per meter squared? So this will not be the same thing because it's not a comparison between two. You're not saying one is twice as big as the other. This one actually gives you the intensity of 2.5 times 10 to the minus 6. And so in that one, you're going to actually have to do like they do here and actually calculate it. So you have to actually calculate the intensity. And so it's going to be something like 2.5 times 10 to the minus 6. It's going to be something in the 60 to 70 range because this is 1 times 10 to the minus 6, right? And you're looking at 2.5 times 10 to the minus 6. But you're going to take this number and you're going to plug it into this equation right here for I. So you plug 2.5 times 10 to the minus 6 in for I. I0 is this number right here, 1 times 10 to the minus 12. So you plug in 2.5 times 10 to the minus 6, divide it by 1 times 10 to the minus 12, take the log of it in your calculator, log base 10 of it on your calculator, multiply it by 10, and that will give you your decibel. Okay. Any more questions?
I have a question on question 4 on 6 through 10.
6 through 10, question 4. Didn't we just do that? What did we just do?
Question 3.
Question 3. Too close for memory. Question 4. Ah, yes, this is a classic. You have a box that's going to slide down this frictionless hill, and then it's going to hit this friction track here, and it's going to slow down along this track, right? They want to know 2 things. What is the speed of the bottom at the bottom of the frictionless part? So from the slides here down to the bottom, what's the speed going to be down here? And then how far is it going to slide along this part? The key to this question is energy. Do not try to do this problem using forces and kinematics. That will make a mess. You can do it that way, but it'll take so much longer. So much more work. So we want to use energies at the top of the hill before you let it go. What kind of energy does it have? If it's not moving, you're still holding it still, does it have any kinetic energy? No, because kinetic energy is moving energy. At the top of the hill, is any work being done on it? No, because it's not moving. To have work done, it has to be moving, right? So what kind of energy does it have up here? Potential energy, right? So potential energy is equal to mgh. And let's go ahead and open up a little whiteboard thingy here. So we've got our hill here and our friction down here. Okay. So at the top, it's got potential energy. There is some height. And potential energy is equal to mgh, mass times gravity times the height of the box above the bottom. That's also equal to the total energy. We'll just call that E. That's the total energy at the top is all potential energy. Now when the box gets down right here, right before it hits the friction, what kind of energy does it have? If this is our 0 point, if this is height equals 0, then, and it's at the bottom of that height, does it have any potential energy anymore? What does it become? What kind of energy is it now? Kinetic energy. Kinetic energy equals 1/2 mv squared. And that is also equal to our total energy again. So if this is equal to our total energy at the bottom, and this is equal to our total energy at the top, and there's no friction to take the energy out, then this one has to be equal to this one. So for part A, you're going to solve the equation mgh equals 1/2 mv squared. Then you're going to solve it for V, because that's what they want to know. And you know everything in there except for V, so you're good. Now, after you've gone through the friction part and it is now stopped, velocity equals 0. There's no kinetic energy. There's no potential energy. Where has the energy gone? The energy escaped the system somehow. How did it escape the system? Well, usually when energy escapes the system, it's through heat. In this case, it's friction that causes the heat, right? So friction happened through here, and friction does what we call non-conservative work. So work is equal to force times distance, right? And the work that is done has to take all of this energy out. So it's also going to be equal to our total energy. So the energy that we calculated at the very beginning is now going to be equal to the force times the distance. So the mgh is going to equal the frictional force times the distance. Now the only thing we don't know in this equation is the distance, but we have to calculate the frictional force, because frictional force is equal to mu, the coefficient of kinetic friction, mu kinetic, times the normal force, right? And since this box is on a flat surface with no forces acting up or down except for its weight, that's the kinetic coefficient of friction times the mass of the box times gravity equals the original. So this goes back up to here. So this equals mu k mass times gravity times the distance it travels. And we know mass and gravity, and I think they give us mu k. They should. Yep, they tell us the kinetic coefficient of friction there. So then we're good. We're good to go. Now you plug them all in. So first you use this equation and this equation to solve for V. Then you use this equation and this equation to solve for D. And then you're done. Now, always remember that there are questions that can be solved using energy that don't require you to do kinematics, because that will save you time and pain, right? This is a much quicker, this is just two quick equations, pretty much done, three quick equations, I guess. And there's no like solving simultaneous equations or anything. It's just solve one, solve the other, be done. Whereas in kinematic equations, it's often multiple equations, multiple unknowns, solving them simultaneously. But sometimes multiple dimensions. This could be multiple dimensions because it's got up and down and side to side. All right. Who else has a question? Anyone? Yeah.
Question
Keep. Question number 9. All right. Here?
Yep.
Ah, man, this one's good. Now, there is a little bit of a thing that you need to remember that applies directly to this situation and will help you to shortcut this situation. So let's go back to our two-dimensional kinematics and figure out what that is. If we do a two-dimensional kinematics with right here. No. Here. That's not right. Gotta be this one. Nope. Try this one. Okay, so in this one, I think they do this problem somewhere, maybe. No, they don't. Is it two-dimensional dynamics? Oh, no, it's this one. Yes. Momentum. Yeah, that's what it is. That's right. So collisions in two dimensions. That's what it's from. Okay, so they do this problem in the book right here where they do this conservation of momentum. Now remember, the momentum is conserved in both the x direction and in the y direction. So is there any momentum to begin with in the y direction? No. And what that means is that any momentum that this ball has going this way, this one will have the exact opposite momentum going this way. Remember, momentum equals mass times velocity. And it does care about direction. So if this is positive velocity and this one's negative velocity, then they can add together to be 0. However, if these balls all have the same radius and all have the same mass in a frictionless system, there's an interesting result that comes as they go through this. They're working through it, and then they solve for the angle between these two. They solve for this angle here, theta 1 plus theta 2. And when they do that, they get an interesting result if you have the same mass. And this is the interesting result. That theta 1, they're calling this theta 1 minus theta 2, but anyway, it's still theta 1, it's still the total angle between the two. It will be 90 degrees. In other words, if you have a ball that comes in and hits another ball and they're the same radius and the same mass, it hits another ball and they glance off each other and go off in different directions, this angle here will always be 90. Now why does that help us? That helps us because if they give us one of the angles to the middle, we can calculate the other one just by taking 90 minus the first one, which is exactly what they do in this problem. In this problem, they tell us that theta 1 equals 28, right? And they have all these balls have the same mass, they're the same radius, they're all billiard balls. That means that if you take 90 minus 28, you will actually get 62 for your other angle, which is the answer right here. If I type in 62 right here, I'm done with that part. Got it. Now all I have to do is calculate velocity 2. Well, that's a little bit different. That's a little bit, we're going to use this angle here, and that's going to really be helpful. But we're going to have to do a little bit more now. So, go to our whiteboard. Have our ball here coming in, hits the ball here. This one goes up this way. This is ball 1, ball 2. Ball 1. I think ball 1 goes down, but anyway. So this one has velocity 2, called velocity 2 prime, velocity 1 to start off, velocity 1 prime. But velocity 2 and velocity 1 have components. This one has velocity 1x prime, and this one has velocity 1y prime. And this one has a component, velocity 2x prime, and velocity 2y prime. Now, it may look like these are, equal, but they're not. They're not equal. We don't have any reason to suspect that they're equal. This one is 28 degrees, which is a lot smaller than the angle that I drew in there, but this one is going to be 62. Right? Oh, I did it wrong, actually. Let's go back and change that real quick. They say this is actually ball 1. So this one's ball 1, and this one's ball 2. So we change all these to velocity 1, velocity 1, velocity 1, and make this one velocity 2. Right? So anyway, but still I got the angles right, I think. Yeah, I got the angle right. So, now what we're trying to figure out is what is this velocity here, I think, right? What do they ask me? They want to know velocity 2. So we want to figure out what is this bottom velocity here. Well, let's use the components. We know that velocity 2y has to equal the negative of velocity 1y, right? Because this one has to cancel this one out. Just like this one and this one have to add to be, like, well, not the velocities, but the momentums. What we know is that the momentum is conserved, so if we have the momentum in x, the change in momentum in x has to equal 0, and since at the beginning there was 0, that means that the sum of all the momentums afterward have to also equal 0 in x. So we have two momentums in x. We have, we'll use y, not x. This is not y. Not x, in y. So both the momentums in y have to equal 0. So the two momentums that we have are the momentum of 1 in the y direction prime afterwards, and the momentum of 2 y prime afterwards. We happen to know that the velocity of 2 is negative, so we'll just go ahead and write that as a negative, put a negative in there just to make sure we've got it, because we know that one's going to go down in the negative direction, this one's going to go up in the positive direction. So what is the momentum of the first one? Well, the momentum is the mass times the velocity, so it's mass 1 times the velocity, or we'll start with mass 2 actually. No, we'll start with mass 1. So this one's mass, so velocity. So velocity 1 in the y direction, what does that equal to? Well, it's the side that's opposite the 20-degree angle. So this is going to be velocity 1 prime times the sine of 28 degrees. And this one here is going to be velocity 2 prime times the sine of 62 degrees, and that one's the negative one, but we already put the negative down here. So for the momentum 1, we have mass 1 times velocity 1 times sine 28 degrees. And then we subtract, because this one is going down, it's negative. We subtract V2 prime sine 62 degrees. Well, we have to put in our mass too. sorry, I'll do a minus here, and this will be mass 2. So mass 2, V2 prime sine 62 degrees. Can't write. 62 degrees equals 0. So this equation right here can be solved. We know everything in this equation. Let's see, what do we know everything in this equation? Yeah. So we know that the first one, V1, continues at 1.68 meters per second, so that's V1 prime right there. And then we're solving for V2 prime. And we're done solving that. So, does that make sense?
Yeah.
Any more? Anybody else have any more? As soon as we're done here, we're done for the day. So if you don't have any more questions, we can call it a day. If you do have more questions, we can answer them. Any problems you want to do? Any topics you want to cover again?
I have one on 13, but it's kind of like 4.
It's chapter 13, number 4?
No, the same thing.
13?
13.
Oh goodness, it's got me all whacked out now. Alright, so still 6 through 10,
Yep.
number 13. So this one is very similar to the sliding box trick, but it's rolling. So when things roll, they have more than one kind of energy. You can have kinetic energy due to your movement, but you also have rolling kinetic energy. So there's two kinds, a rotational kinetic energy and a linear kinetic energy. At the top, there's still just potential energy. But when you get to the bottom, you have to add two kinds of kinetic energy. So in essence, when a ball gets down to the bottom of a hill, rolling down, it actually will be going slower than a box that slides down with zero friction. Because rolling takes some of that potential energy and turns it into rolling kinetic energy. Right? So wheels essentially will slow you down compared to like a frictionless slide. Right? If you try to go mountain biking down a ski slope in the summertime, you'll never reach speeds that skiers go down those slopes in the wintertime. Skiers go down way faster, especially if they're going straight down. So that's because the mountain bike has to use some of that potential energy at the beginning to get its wheels rolling. So anyway, the idea is at the bottom, they want to know what's the linear and angular velocity of the solid sphere at the bottom of the curved track. So they want to know how fast it's moving along, how fast it's moving forward, and how fast it's rolling around. And they want to know how high it will roll up the other side. And they're assuming that there's no friction. Well, if there's no friction, we can immediately answer this second question, this question right here, can we? What is the answer right here? Because if there's nothing taking energy out, then it will gain that potential energy back on the other side. Right? This velocity and this omega are the big question marks. So let's take a look at those really quick. Oops, apparently I already had it open. All right. So, here's our track thing, whatever. Not really good at that. Up here we have all of our energy equals potential energy, which equals mgh. And then down here, the ball has linear kinetic energy from moving forward, but it also has this rotational kinetic energy. And we have to add those two together to get the total energy. And of course, linear kinetic energy is 1/2 mv squared. Does anybody remember what rotational kinetic energy is itself? I'll start at 1/2 Instead of v, what do we use for rotational velocity? There is an r involved in this equation, but it's not immediately apparent. Instead of v, we use omega, right, for rotational. And instead of using mass, like we do in linear stuff, we use the moment of inertia. Remember the moment of inertia? Now we have to go and see what kind of thing this is. This is a solid sphere. We have to know what kind of shape it is, because then we have to go to our book and we have to look up the moment of inertia for a solid sphere. So that's going to be in rotational motion, angular momentum, and we're going to look at rotational inertia right here, moment of inertia. Then we're going to come down here to this chart with all the shapes on it. And we're going to look for a solid sphere. Solid sphere is right here. A solid sphere's rotational inertia is equal to 2 times the mass times the radius squared over 5. So 2/5 mr squared. So we go back. I is equal to 2/5 mr squared, total energy, which also happens to be equal to our potential energy at the beginning, mgh, is going to equal 1/2 mv squared plus 1/2, and then our I, which is 2/5 times the mass times the radius squared times omega squared. Now, we're still not quite done with this. You mentioned that there's an R related to this, and you're absolutely right. If the ball is rolling and not slipping, then the linear motion is related to the rotational motion by R. And it looks like this, where the linear motion, V, equals R times omega. So if we solve this, we get omega equals V divided by R. And we can plug that in right here, and we will get, instead of omega squared, we will get V over R squared, V squared over R squared. And then we have an equation where we know everything. We know M, we know G, we know H, we know 1/2 and M. We don't know V, but we're going to learn that one. And then we know all this other stuff except for V. So we can solve this equation for V. And then once we've solved that equation for V, we can calculate omega from that one. We're done. So speed is always equal to frequency times wavelength. The wavelength is going to be related to the length of the tube. So what I would do is calculate the wavelength of these each first. So what kind of tube was it? I forgot. Open at both ends. So we're making organ pipe tubes that are open at both ends. When a tube is open at both ends, you essentially you can fit a half of a wave into it. So the length of the tube is going to equal 1/2 of the wavelength. Right? And wavelength times frequency equals speed of the velocity of the wave. So they've told you the velocity of the wave, and they've told you the frequencies. So you just need to calculate wavelength, which equals velocity over frequency. Once you've calculated each wavelength, Then you need to plug it in this equation and solve for L, which means you need to multiply each wavelength by 2 to get the, no, sorry. You want to calculate L, not wavelength, right? So you need to take each, you need to just plug it into this equation and calculate the length. So it may be that you just forgot to calculate like half of it.
Yeah, I just did the first part.
Okay.
So I think I just got
Yeah. Okay. Anybody else have a question? My brother played in a marching band, I guess you could call it. They call them drum and bugle players. But it's interesting because they do these. See if I can remember the name of his drum and bugle corps. It's called Santa Clara Drum and Bugle Vanguard, right? And they did. I want to say it was Nutcracker or something. Long time ago, not the Nutcracker. Yeah, so it was 95, that sounds about right. And in this show, you can't really see it really well. But down here on the ground in front, they have a bunch of percussion instruments. And they created this new percussion instrument for this show. It was essentially just a big piece of PVC tubing, and it would go down to the ground and lay it all along the ground. And I think that's what you're seeing, this white strip here. There's a bunch of these tubes, and they essentially just made these big padded like whack-a-mole things, and they just hit the top of the tube, so it sounded like this boom, but it's different sounds. So it's boom, 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 boom. But they had to make them just the right length, and I wonder if they calculated it, or if they just made it a length and then you cut it to fit. Cut it and then hit it again. I wonder. But anyway, that's just kind of a funny thing. They were quite good. They go to these international shows and compete against people from all over the world. Like they're better than any university band by far. There's not even a competition. There's not a university band out there that can even enter these competitions. They're that good. But anyway, a lot of fun. Lots of fun. Anyway, no more questions? Are we all done?
I
Do you have it on?
So
Okay.
if it was closed, then.
So for a closed end, so this is how I remember these things, the closed end, open end thing. This is not exactly the way the book does it, so I try not to confuse you by using mine all the time, but maybe this will help. So on an open end tube, I think in terms of how much the air can move, right? If it's open at both ends, the air is free to move. It can go out and in, come out of the tube, and go back into the tube, and so I use this scale. So this is my center scale, center line of the scale. And I say if it can move outside the tube, then this is a lot of movement up here. It's a lot of movement in the positive direction. So the air can go up from here down to here, from here down to here. So this is the extreme end of its movement. And on this end, it can move as well. But if this end is moving on this side, this end will be moving on this side. And then I draw a curve in between there. And that shows me 1/2 of a wave if I continue that. That's half a wave. From this point back up to this point again, half a wave. That's how I do it. For a closed end tube, so this end is now closed off. It has a cap on it down on this end, right? On the open end of it, it can still move around a lot. So the start's up here, but on this end, it has to go to 0. This is my 0 point right here, 0 movement. Because at this thing, the air just gets trapped against that wall and it can't move, right? So this has to go from open to closed. And so if I continue drawing the wave, it's going to go all the way down here and then have to go all the way back up here and way off the screen over here. And this ends up only being 1/4 of the wave. So in this case, the length of the tube is equal to 1/4 of the wave for the fundamental. And in this case, the length of the tube is equal to 1/2 of the wave for the fundamental. Now, you can continue to fit more waves in as long as it fits this pattern. This has to go from extreme to extreme or extreme to extreme, so I can actually fit this wave in there too. And so but that's a harmonic, that's the next harmonic up. But I could also fit this one in, it goes like this, because it has to start or end, top or bottom, because it has to be at the extreme ends. And this one has to start at the extreme and end at 0 every time. So I could get this wave in there too, which is 3/4 of the wave. Or I could get this one in, which is 5/4 of the wave. And they show you this in the book, but they show it to you a little bit differently. But it's still the same idea. And so then you have the two formulas for each of those. That help any of those?
Yeah.
Any more questions? If we're done, we're done. Record time. Have a good day. Good luck on your final exam. I will be answering emails today or tomorrow and Friday as much as I possibly can. You know, it's best if you get all your questions in tomorrow, if you can, just in case. Because I think the testing center is open on Friday. I know that because my wife is working there. So if you're taking the test on Friday, you'll get to meet my wife. But I'm not sure about how busy they are or anything. I'm assuming they won't be very busy. But make an appointment, since it's the end of the semester. A lot of people will be taking tests in the summer. And good luck in all your future schooling and endeavors. If you ever want a letter of recommendation, because sometimes you need those from teachers or anything like that, feel free to send me an email. If you ever have any questions about anything else, feel free to send me an email, call me, come back, whatever. I enjoyed having you in my class. Have a great summer.
Thank you.
My pleasure. Thank you.